Hi everyone and welcome to today's lecture. This is Pranav Kulkarni and in this lecture we'll be discussing about complexity analysis. Now we know what an algorithm is, how we design an algorithm, how an algorithm works. But as the size of the input increases of an algorithm, we have to keep two things in mind. How much time does a particular algorithm take and how much space does it occupy? So to answer these questions, we need a comprehensive study so that we can optimize the algorithm on basis of time and space so that we build a proper system where everything is optimal and thus it gives the desired results we want. So the basic question that comes in, why do we have to study a particular theory to analyze algorithms? Why not just use a stupid watch to do that? Why do we have to develop a theory that is completely different? So for that, these are the following reasons. If you are running an algorithm on two different systems, the hardware is different, the processor is different, the memory is different, which does affect its timing. The operating system on one may differ from the other. The version of Java or Python, the libraries, the drivers, the programs you are running in the background. If you have a heavy program running in the background, it may affect the time the algorithm takes to complete. If the what the implementation are you using of a particular algorithm? What size of input are you using? The number of inputs in that instance. These are a lot of factors that affect the timing of an algorithm. That is why we have a different set of rules when you're analyzing it. Timing does have its own place in algorithm analysis, but it comes into picture when you want to check if an implementation of an algorithm is optimal or not. That is where you use timing. So if you're calculating now when we are comparing two algorithms, there can be many measures of comparison. The very first is security. We need to make sure that the algorithms we are writing should be secure. The second one should be clarity. The algorithms you are considering writing or consider analyzing should be clear enough so that they can be implemented or can be analyzed. And the third is performance, and that is what we are focusing on here. So when we are analyzing performance, there are three things that have to be kept in mind. The first, that we have to analyze the algorithm for larger inputs as well, because every other algorithm is pretty good at smaller inputs. The answer should be independent of the CPU speed, the programming language, the coding jargon. So it doesn't matter if you're coding it in Java or Python. The analysis or the performance of the algorithm should be independent of whatever language you're using. The answer should be general and rigorous and complementary to coding it up and timing it on some test cases. Now, before we start analyzing a particular code, we have to keep in mind assigning a particular value to a variable, assigning one variable's value to another is all an operation that takes constant time. Accessing an element in an array through its index, comparing two values, assigning one value to the other are all basic operations that take constant time. Now, the whole complexity thing comes into play when we're using loops. So, when we're using loops, there are two factors that have to be kept in mind when you're analyzing the complexity of it. One, the cost of the loop body, and the second, the number of loops that are involved. One operation, one thing that is to be kept in mind when you're calculating complexity inside loop is there is something accompanied with a loop, and then it also depends on what number of loops you're using. It all adds up to the complexity, and that is why loops is something where the cost of the loop body and the number of loops used are taken into account when you're calculating time complexity. A worst case analysis. In general, there are three types of performances: the best case, the average case, and the worst case. Let me give an example to explain this. Suppose you're given an array, you have five elements in it. What's the best, and you have to search a particular element in it. What's the best case scenario? When you enter an array and find the element you're searching for, that's probably the best case scenario, right? The average case scenario would be you find the element somewhere in between the first and the last element. And the worst case scenario would be that you don't even find the element after passing all through the array. That is the worst case. While calculating worst case, we may become pessimistic, but we have to remember worst case is the baddest the algorithm can do. It's the worst timing that it can register. And computer scientists have established that this is something that is probably very good to a very a lot of computer scientists have established that the worst case timings are probably a benchmark to calculate the analysis of an algorithm, because that's the highest time an algorithm can take, or that's the lowest an algorithm can go to. When we calculate an algorithm, we have to keep in mind that we have to only take in amount the most dominant terms. So for instance, for 6n square and 20n square, the big O will always be n square and not the other constants that are accompanying with it. Now there may be a question on what big O is. So to explain it mathematically, for every n greater than n naught, g of x is called the big O of f of n. That is what it denotes. It denotes that g of n is the worst possible performance of f of x under values that are greater than n naught. That is the connotation that we use for big O. Now the whole gist is to consider the most dominant term. So if your function is fn of 3, the big O will be O of n. If your function is 7n plus 5.5 n square plus 2000, your big O will be n square and so on. Now something that is to be kept in mind is that you should not play mess up with the powers, and we should not the main thing that is to be kept in mind that you should not mess up with powers. The big O of n cube is not O of n square, and big O of 3 of n is not O to the power n. This is the general consensus on how fastest to slowest the average big O values are. Now this something that is to be remembered is that this is only valid for n greater than n naught. We start from the fastest, that is O of n, and then comes O of log n. Then we move on to n, then n log n, then n square, then n cube, then n to the power k, and then k to the power n. Now this is a graph which shows on how much time does a particular thing take. So for instance, if the size of the input is 1024, the log n may take 1 second, but the complexity big of nk would take approximately 1.2 days. So this is something that should be kept in mind while designing. You should design an algorithm that has a time complexity of log n, so that it processes the input faster. It gives you a proper value as an output. Now, this is something that we discussed earlier, but I'd like to throw more light upon it, that the big O notations are only valid for n greater than n naught. It may differ for n is less than n naught, and that n naught is to figured out by the designer who's analyzing the particular algorithm. So, for instance, uh, quicksort's algorithm. So, for instance, quicksort's big O is n log n, and the insertion sort is n square. So, by theory, quicksort should be better than insertion sort. But in reality, insertion sort is faster for smaller n's. So much so that good quicksort implementations switch to insertion sort when n is less than 20. This is a general consensus. We say that 3 of n square, if the overall cost of the loop plus a number of loops involved, you get an arithmetic value of 3 of n square plus 17, then it's denoted by big O of n square. Now this is a general definition of three terms, that is big O, big omega, and big theta. Big O is called the upper bound, which denotes a set of all functions asymptotically less than or equal to f of n. Big omega is the set of all functions asymptotically greater than or equal to f of n, and big theta is the set of all functions asymptotically equal to f of n. Let's explore amortized analysis now. So what happens when we have a costly operation that occurs sometimes but not every time? So for example, you were to add an element to an array, but then you were to add elements to it dynamically. So if the array is full, you have to increase the size and then add it. Now one of the procedures can be to double the array size and copy the old array into the new one. Now this will help us to explore how amortized analysis works. So this is an example of a function where we call a function called putx. So if the max size is equal to count, We make a new array of size twice the size of the old one, copy the elements of the old array into the new array, and then add the exit at the end, and then we increase the counters accordingly. So if we calculate the performance of PUTX, it is usually make the array of the bigger size, copy the old array, and update the maximum size. So in this way, we do not have to enlarge the array each time we call it. There would be only be instances when the array is full and then we have to enlarge it. So we certainly have an average of a situation where we only increase the size of the array when we require it, and but the complexity changes. Now addition of an element to an array is not O of n, it is theta of n, which is an average of O of 1 and O of n. So this was all about amortized analysis. We'll further solve questions called buy and sell stocks, which will help us understand the complexity of a particular algorithm practically. I'll explain the problem and show you two approaches on how you can solve the problem. Cool. Problem 121, call best time to buy and sell stock. So let's read the problem. You're given an array of prices where prices I is the prices of a given stock on ith day. You want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell the stock. Now you have to return the maximum profit that you can achieve from the transaction and return zero if you cannot achieve a profit. Now these are some examples. Now let's say your prices are is 7, 1, 5, 3, 6, 4. So the maximum profit will be when you buy on day 2, that is here, and sell on day 5, that is here. So the profit is 5. Now, by the basic understanding of the problem, a brute force method that comes into our mind is to calculate every single values possible. So you start your pointer at 7 and then calculate the profit for 7, 1, 7, 5, 7, 3, 7, 6, 7, 4. Then you increment the counter, go to 1, and then calculate the combination profit for 1, 5, 1, 3, 1, 6, 1, 4. Then you keep your pointer at 5 and then calculate for 5, 3, 5, 6, 5, 4, and so on. This involves the following algorithm that has the time complexity of n O of n square. So in that, the outer algorithm runs for n time and the inner runs for n minus 1 times. So the complexity is n square plus n. Now as you remember, we have to only consider the most dominant term. So the overall complexity of the problem turns out to be O of n square. You cannot directly copy and paste this solution. I use a different custom testing bench for this solution. So if you submit this, you see that the time limit is exceeded because the complexity is O of n square. Now let's try to optimize the following solution. We'll keep a left pointer at the 0th position and the right pointer at the first position. We'll initialize a variable called max profit, and then the length of the array is the length of the array prices. Now if the array is completely empty, no profit can be found and you return 0. Else you move the right pointer such that it should be less than the length of the array. Now if you calculate, if the price at the right pointer is greater than price at the left pointer, you calculate profit. Now if this profit is greater than the previous profit, you replace the previous profit inside the max p with this profit. If not, then you switch the pointer from left to right and continue the cycle. So in this way, we only use one loop and enhance the solution. So if you submit this, the solution is accepted, and then this is how you optimize your algorithm. The earlier algorithm was O of n square, and this is the algorithm of O of n. If we look at the time complexity, try and submit the following solution. It takes 858 milliseconds and it takes 27.3 MB of memory. So this is quite a proper solution to this, and this is how you optimize different algorithms, how you calculate complexity and then solve particular problems through it.